Okay, so the things that we need from parametric equations are, of course, these things here. You have to know the speed of a particle on the path. You need to know that equation. You need to know how to calculate the slope of the path. And you need to know what the x and y equation represent, and then the x prime and the y prime. You just have to be able to do that. On the homework, questions 1, 3, and 5, it talked about direction of travel and tracing and graphing on your calculator. So therefore, if you have a picture on your calculator that looks like this, I think that was one of them. When it says mark the direction of travel, we're just looking for something like this. Okay, some arrows on the thing tell what direction the particle is moving. You can get that by tracing. If you can't see it when it graphs, you can trace. Type in a 0 or whatever your beginning t value is. Hit the right arrow and see as it goes along. If it asks you to label some points like t equals 0 or t equals -1 and 1, you know, something that looks like that. That's what we're talking about for those, you know, mark the direction of travel and label points, which means this is where the particle was at certain times along the path. Okay? In number 6, my intention on number 6 was for you to take the x equation, 2 plus 3t, and y equals 1 plus 2t. You were supposed to eliminate the parameter and get y in terms of x. My intention was, this is where you would solve for t, okay, divide by 3, like so, substitute that back in, because we always want y equals, so you do the x equation, then you substitute it in here. 1 plus 2 times this, maybe go ahead and distribute and simplify, and then that be the answer for that. And then the other part was they asked for the beginning and ending point, so you put a 0 in here, and you get the 0.21, and you put a 1 in, and what'd you get, 5, 3? Is that right? So they wanted the beginning and the ending point, and so do that. Now, I had a few people tell me what they did is they went ahead and just graphed it, and on our next quiz, it'll be all calculator. You'll get to use your calculator. So they just went ahead and graphed this parametric equation, traced at 0, got this, traced at 1, got that. That's fine. I'm not making you write out the 0 and write out your work for that. So if that's what you did, I'm okay with that. And then they also just looked at the line that was on their paper or on their calculator, and then just said, well, the slope is 2/3, and one of the points on the graph is this, and then they just wrote the equation line that way. And I'm okay with that too, and that's fine. The directions were eliminate the parameter, write y in terms of x. I do, though, just want you to be aware of this way of doing it, okay, that you can solve for the t and substitute that way. Now, solving for the t and substituting doesn't always work, though, right? Sometimes you get an x equation that you can't solve for the t, so you have to be creative. Now, we're not going to spend a lot of time doing those, all right? But here's an example. I did one similar to this when we were talking about unit circle, although I didn't really approach it from that standpoint. Here's the unit circle. And if we wanted to put that in terms of just x and y, I think I showed you, hey, this is the unit circle. I showed you how it connected to the equation. Remember we did x squared plus y squared equals 1, which is the same as sine squared plus cosine squared equals 1, right? But if I gave you this and said, eliminate the t and get it in terms of y and x, what would you do? Well, you could actually, this one you could solve. You could do arc cosine of both sides. Then you could plug that in, have sine of arc cosine of x, but then you would have to draw triangles and things, and that's not real easy. You could do it, but it might be difficult for many to do that way. So you can be more creative. There's some other things you can do. Now, this is actually what you were supposed to do in number 11, part B. Number 11, part B, they said show how these equations became this, right? Well, here's the technique, okay? On number 11, part B, subtract A from the x equation, subtract B over to the other side of the y equation, okay? Now, square both sides. So this one, I'm going to do it with this example up here, but you could do it with number 11, B as well. So square both sides. Why would I square both sides? Because I know there's something special about sine squared and cosine squared, right? That's what might make me think to do it. Now I'm going to add those two together. Now, that's just an algebra thing. Whenever you have two equations, if 3 equals 3 and 5 equals 5, then 8 is going to equal 8, right? Okay, so anytime I have two equations, I can add the two together and they'll be equal. So I get x squared plus y squared equals cosine squared plus sine squared, which is x squared plus y squared equals 1. I got the parameter to eliminate by just being kind of creative. Okay, so the t disappeared. So those are some things that you can do in some problem. Now that's not going to be a huge part of the quiz, but just understand that's something that we can do. This idea of substitution, you know, here we did a substitution basically, cosine squared plus sine squared is 1. All right, well, if you do that same thing with number 11, part B, you get r squared, factor it out, you get this, which would be 1, and you'd have x minus a squared, y minus b squared, and all equals r squared, which is just a circle shifted with a different radius. And we talked about that. If you took the unit circle here and put a number in front of the sine and cosine, that would just change the radius. And then if you add an a and add a b, that just shifts the center around is all it does. Okay? So, there's that. Something we should be able to do. Okay. Then I wanted to talk about 17, 18, and 19, or 17, 18, and 20. And we talked about that yesterday with the baseball. Let's focus here on number 20, because 17 and 18 just really refer to the same problem we did yesterday, just changing some of the numbers. So 20, the interesting thing about 20 is that we go ahead and put in the wind resistance, which makes this much more realistic. So I would write the equation, I would rewrite, I've talked about this before. If I was writing that x equation, I would write it this way. It's going to make it a little easier to handle, but since you're using the calculator, quite honestly, you don't need to do this. But here would be the baseball with the wind resistance. What we've done is we've taken, and like we said, the horizontal now, the wind resistance is going to be a big factor in slowing the ball down horizontally. Little bit vertically as it drops, but mostly gravity's working there. The wind resistance is more in the horizontal. So we've put it all into there. Okay, and if you read the problem, they also discuss how there's that K value in there, right? There's that K value in how smooth the ball is going to affect the wind resistance. And so all those factors are wrapped up into the K value that they've used. Okay? All right, so this makes it a little more interesting, and we have our equation. But otherwise, from this point on, it's exactly the same that we did yesterday. Exactly. It's all the same questions. Part A, at what time does this ball cross the plate? What do we do? Put 60.5 right in there for x, because when the ball is across the plate, its x coordinate is 60.5. So we put a 60.5 there, we get on our calculators, we do a solve, and what do we get for t? 442. Okay? Now this is the thing I was trying to get across yesterday. If you hadn't already spent some time thinking about this and looking at this, yeah, okay, and tried it on your calculator, you can watch it and you can shake your head and you can go, oh yeah, okay, that makes sense. Well, what are the chances now in a quiz 8 days from now and you have to do this that you'll be successful? Yeah, I don't know. Okay. 0.442. Next question is, how different is that from what we did yesterday, right? Than the example. What was the answer yesterday? 0.403. It takes a little longer to get there. The air resistance slows it down, right? Okay. Part B. At what height is it when it crosses the plate? Put that number right in there and see what the y is. And it's what, 3 point something?
3.86.
Another thing I noticed as I went around is, you know, somebody's got 2-3 pages worth of work. They're writing their equations out. They're showing their work. Get in the habit of doing it. That's what you have to do on the homework problems, right? You need to write this equation, even though we are doing it on our calculator. There are plenty of papers I looked at that just had t equals 0.442. That's not what you want on part A. You want this equation written out, then go to your calculator, solve it, put down the answer. Okay? In part B, you want to have y of 0.442. You probably had better use more decimal places than that, but this at least shows what you're doing there. Now go ahead and go to your calculator. It was 3 point what?
871.
7057.
Okay. So it's not as high as the ball, right? So since it's slowed down more, then gravity has more time to take effect. It was like 4 point something the other day, right? So 3 points. So this one probably is a strike. This one would be probably right in that strike zone. And what speed does it cross the plate? Okay, that goes back to that speed equation that we talked about earlier. Okay, the x prime squared. So what's x prime? The derivative of this, right? Right? Now, on the quiz, what would this need to look like? Because you get to use your calculator, right? You can let the calculator do that derivative. I'm okay with that. That's fine. Okay, but you need to at least put, you know, down the result here on your paper. Now, just for some practice here, let's do it. This is why I wrote the 1,000 over 3, because that's just going to set out there times, what's the derivative of natural log? 1 over the inside left alone, which would be that, right? Times the derivative inside, which would be 0.45. That's x prime, right? Then you need to do what with that? Well, you square it, but what else? Well, but don't we have to plug that in? Right, we're trying to find the speed at the time it crosses the plate, right? Well, this is the time it crosses the plate. So we need to plug this in and then square it, okay? And we're putting it into this. So again, on your calculator, there's our x prime. We're going to plug that number in, see what that is, probably write that out instead of x prime. I would write that number out. Again, probably use, when you write it on your paper, I don't care, put 3 decimal places, that's fine. On your calculator, you might want to keep more than that, okay? So you're going to square that, plus now we need y prime. What's y prime?
32.
Negative 32t. See, so if you had on your paper, as some people did on number 20, part C, if you just had an answer, see, that's, you know, you probably wouldn't do that on the quiz anyway, but I'm just, even though you're using the calculator for all these calculations, there's stuff that needs to go on your paper. Okay, so there's y prime, so now we're going to stick that number into there, right? And that's going to be here, and then that's going to be squared, square root of all that, and what did it come out to? 125 point, and go out to 3 decimal places and so forth. So much slower. Yesterday it was 150.55, which meant the ball actually sped up, and we talked about how wind resistance would make that happen. But here, this is much more realistic. It is slowed down to 125 feet per second. All right. And then where does it land? What did we do for that?
You take your x.
We take, no, no. Yeah, we take the y equation and set it equal to 0. Because when it lands is when its vertical position is 0. So it will land when the y is 0. So we find that time. And somebody got that? No, the time. 0.66 something. That's the time it hits the ground. Then we plug that back into the x equation because we want to know what its x coordinate is. Where did it land? And that's 86 point something, whatever. 8, right? 86. See, and so there's a lot of doing this and then setting it equal to this and then plugging that back into that. And you just got to think about what each of the different equations represents to be able to do. All right. So that is parametric. Those are the things we need to do with parametric. Certainly they can get more difficult than that. They can be easy ones, there can be some more difficult ones. I've got another problem I want us to attempt with parametric and stuff, but we'll come back to that later next week. It'll be a good chance to come back and review some of these things, because one of the disadvantages of Chapter 4 in each of these sections, like I said, is some separate topic unrelated to the other topics. Well, we're going to have a quiz over 3 of the sections, and they're going to be unrelated. So you're going to have problems that do totally different things. You're going to have to keep that straight and be able to do that. So again, I come back to what I said at the beginning of the period. Spend time in the homework, coming in and asking questions you need to, making sure you really understand that's important, and it's got to start now. See, like I said, you know that. You've been in this class long enough now. It ain't going to start on Thursday. You know, next Thursday, you can't come in and say, you know, I never got parametric equations. Okay? That work needs to happen now. You need to be coming in and talk to me now if you're having difficulty with parametric equations. Okay? Because we're going to move on now to this next topic. Okay? All right. So in your books, if you want to look, it's section 4.3. All right, and the topic here is optimization. We're optimizing quantities. Now, optimize is basically means, you know, the best scenario. The optimum situation be the best scenario. And for our purposes, that's going to involve maximum and minimum. Maximum and minimum. Okay? Now, for example, the business is making a product and they want to maximize their profit. For them, that's the optimum in that case, the maximum profit. Or they might want to minimize their costs. That's the optimum. Or the snowmobiler stranded in the snow who wants to get to the gas station, right? The minimum time would be the optimum for him. Okay, so when we say to optimize the problem, what we're saying is to maximize or minimize. Okay. Now, the calculus part of that, we already know. As a matter of fact, I'll see if I can get this to reach. See if this works. I have my doubts. Okay, so when we talked, everything was going so well yesterday.
Always.
I think it's farther down. Not that far.
Yeah, I guess.
I think it's
Now this.
You should draw.
Now you realize I could have just grabbed this eraser right here and come over there. I just realized it. All right, I know they got that one there for fun. Yeah. So how we doing? All right. So what we're looking for here is the idea, the concept of absolute max and min. Now, on the plus side, there's no new calculus to learn in optimization. We, in Chapter 2, already learned about how to find absolute max and min. So what you'll find out is the stuff on optimization, the only thing new we have to do is apply it to real life situations, okay? Which means story problem, right? Which means setting it up and getting, you know, and dealing with some parts of functions that we maybe haven't had to up till now. But the calculus part of it is not new, all right? So that's probably the frustrating thing about this is you can do the calculus part of it, but you can't do the algebra part of it, right? And so what we're doing is talking about absolute max and min of a function f. Now we'll probably call it different things other than f in our problems. I mean, you can call it f if you want, but whatever. But if we're doing the absolute max and min of f of x on some interval ab, okay, let's just review quickly what it is that we did to do an absolute max and min. There were three, well, you can say 2 or 3 or 4, depending how you want to do it. There were 3 places an absolute max and min could possibly occur. Okay? In this particular picture, where's the absolute max? The right endpoint. Where's the absolute min? The left endpoint. Okay? But if I change this just a little bit, now where's the absolute min? Where do we call that? Local minimum, and what's true at that point? It's a global min, but what else is true at that point? The derivative is 0, and we call that a stationary point. Okay? Let's change it a little bit again. And now where's the absolute max of that problem? At the sharp point. And what's true there? Derivative's undefined. So there are, remember that now? So on a closed interval, for any function, the absolute max or min is going to occur where the derivative is 0, or where the derivative is undefined, or at the endpoints. Now, I usually say there are 3 places to look. Those 3 right there, where the derivative is 0, where the derivative is undefined, or at the endpoints. Now, some people say that that's 4 points. Derivative 0, derivative undefined, left endpoint, right endpoint. And some people would say, no, that's really 2 places to look. You look at the endpoints and you look at the critical points. Remember that term? What's critical point mean? It's 1 and 2 together. This is stationary point. Number 1 is a stationary point. Critical point is 1 and 2 together. So is there 2 places to look, 3 places to look, 4 places to look, whatever? Those are the places to look. Okay? Maybe that'd be a good quiz question. I'll ask you 2 places, then I'll ask you 4 places, and then you have to divvy it up. I don't know. But that's where we look. And then once we look there, in other words, we find x values, right? We find x values that fit those scenarios, and then what do we do with that? We do our list of candidates. In other words, these are the candidates right here, right? Those 3 are the candidates. We take those x values and we do what with them? Plug them into the original, which in our case, in our example here, is f. So we have f of, whatever, f of whatever, on and on. And the point of having a list of candidates is what? To find the outputs that's the biggest and the output that's the smallest. And that's our max and that's our min. And it works great because we can make a comparison there, right? We can make a comparison amongst the different outputs. Whichever one's biggest is the max, whichever one's smallest is the min. What if you only have 1 candidate? What if you only have 1 candidate? What did we say to do? Of course, you can't do a list of candidates if you only have 1, because what? There's no compare. It's not a list. Well, yeah, it is. It's a list with 1 element in it. It's still a list. But you don't have anything to compare it to, right? If you only have 1 candidate, you don't know if that's the biggest output or the smallest or in between. You don't have anything to compare it to. So if you have 1 candidate, then we said it's okay to do a local max-min thing. Remember, number line is just a local max-min. But if you only have 1 candidate, that means that's the only possible max-min there could be. So if it's a local minimum, then it would have to be an absolute minimum as well. If it's a local max, it would have to be an absolute max. That's the only time you would do a number line for a global max-min, is if there's only 1 candidate.
Now, how could you only have 1 candidate if there's always 2 endpoints?
That's a great question. If sometimes in our chapter 2 stuff, I would give you a function but no endpoints. I would say, what's the global max of this function from negative infinity to infinity? And we wouldn't have endpoints. So that would be one possibility. And the derivative might never be undefined, and that's how you could only have one. In these problems, since they're real-life kind of story-like problems, you won't just be given the endpoints automatically. I mean, let me back up just a second. Do you have a question, Derek, or was that kind of the same thing? Let me back up just a second. Yeah, Daniel, go ahead.
Isn't there always like a max and a min? So if you only have one candidate, then it's the max and the min?
No, and then that goes back to Alex's same question. No, you're right. We talked about, yeah.
Oh, so if it has, okay.
Well, no, it's a valid question. We did talk about the fact. Well, I thought we did. There is something called the extreme value thing. We're going to learn more about it at the end of this chapter. But it says that if you have a continuous function on a closed interval, then there is guaranteed to be a max value and a min value. Got to be both. But the key is closed interval. On a closed interval. If you take y equals x squared, but you don't close the interval, you just do from negative infinity to infinity, it has no max value because it just goes forever. It would only have a min. Okay? In some of these problems we may not have endpoints. Matter of fact, your very first homework problem today doesn't really have endpoints. But what we will do in these max-min problems is we will at least discuss endpoints if it doesn't have them. In other words, if it goes from negative infinity to infinity, we'll discuss what's happening in relation to the problem as it goes towards negative infinity and infinity. Okay? So we'll have to consider that possibility. And again, that'll make a little more sense as we get into the particular problems. Okay? So now this is what we learned in Chapter 2. Now, what was easy about that in Chapter 2 was I just gave you the function f of x, I gave you the interval, and then said find the absolute max and min. And so you just went through this process. All right? I gave you the thing that we were going to maximize and minimize, and I gave you the closed interval. When these story problems, like for example the snowmobiler, here's a situation, 6 miles south, 3 miles east. He can walk this fast in the snow, he can walk this fast in the road. Where should he walk to get there the fastest? Boom, that's all the information you need. Right? So, the first step you have to think about is, the first question you have to ask yourself is, okay, what's the objective in that problem? What's the objective? Find the minimum time. Put it into our language, find the minimum time. So therefore, what you need is a time function, right? You need a time equation. The hardest part of these problems is setting up the equation so you can do this. See, we already know how to do this. Well, we better. We need to. We already know how to do this, or should know how to do this. The key is you've got to find the function that we need to do the max and min. Once we have that function, then boom, there we go. Do the derivative, set equals 0, go through all the stuff we already learned. So what we're going to be focusing on is how to get these things set up. All right, so back to this. All right, so we'll leave this up over here. And did I get a new page? Okay. Oh, wait.
7.
None of them work. I just can't throw anything away. All right. All right. Back to this. Now, so in your notes you might want, and I hesitate to say a recipe or a list of steps, follow this, and then you'll be able to do it. You really need to just understand the concept of what you're trying to do. But sometimes it's helpful to have, kind of the steps of what's going to happen. And I'm sure over the course of the next several days, I'll word this multiple different ways. Okay? But basically, step 1 is identify the quantity to be optimized. I can't stress enough how important it is for you to think about this when you do these problems. Okay? again, when we did them in chapter 2, I just said, find the max and min of this function f on this interval AB. You had it all there, and there you go. That's not what you're going to have. So in the snowmobiler problem, identify what it is. It was time. We wanted to minimize. So step 2 then, write an equation slash or parentheses function, which I'm going to explain why I wrote both those in a minute, for that quantity. All right, so in the snowmobiler problem, whatever it was, snowmobiler, I think. Well, in that problem, we would say, okay, we're trying to minimize the time, so I need to write a time equation. So I would call it T of X or whatever. You call it F of X if you want, but a lot of times you use the letter that's involved. So that's your goal, that's your objective then, is to write an equation for the time. And if you remember, that's what we did. We said, okay, time is distance divided by rate. So we drew a triangle, we found the distance that he would need to travel, and it was a big square root mess kind of thing. We took that distance divided by the rate in the snow, we took his distance in the road divided by the rate in the road, and add those together, and that was his total time. That was the time that it was going to take you. Then, and only then, are we then ready to go in to this step. Then we have our equation, we identify our midpoints, now we're ready to do the calculus part. Okay? And again, as we go through the homework, I'll be helpful, but I'll try not to be too helpful. Because if I always help you get started on every problem, that's the hardest part of these, is getting started. Now the quiz, I won't be doing that. So you've got to really you've got to get started. You've got to be able to set up the equations, you know, because that's the key part of it. We'll just assume we can do this part right. Okay, now we'll practice that, obviously. That might be an assumption we shouldn't make at this point, but yeah, we'll get into that as we practice. All right, so let's do this problem right here. We already did that snowmobiler problem. So way back at the beginning of the year, I gave you this What is Calculus document. You don't need to pull that up. I don't even know if you still have it. But it talked about optimizing. In other words, they might want to help a manufacturer find the optimal shape that will minimize cost. Okay, and the particular problem we looked at was this one here. You remember, for some of you, it froze up your calculators when you tried to do it. And what we're saying is, if we have a sheet of paper, let's say it's a, 8.5 by 11 sheet of paper, I want to cut out squares out of all 4 corners and then fold up these orange edges to create a box. I would like to find what size corners I should cut out that will give me the maximum volume. Now here I've got a little graph of the volume, and we can tell that looking at the volume and looking at the graph that right in here it looks like is about the maximum, somewhere in that range. Now, I don't think this is set up with 8.5 by 11. I'm not sure what it's set up with, so our answer is not going to come out the same as that. That's the problem we're going to do right now. Okay, so I would draw a picture of the situation. So you might want to go ahead and we'll do this as an example here. Now, I'm not going to put that in my list. I know sometimes when I made a list, I put draw a picture. You know, sometimes drawing a picture is helpful. Many times drawing a picture is helpful. Okay? Step 1. What are we trying to optimize here? Trying to find the max volume. So step 2 tells us we need to write an equation for volume. Right? Again, cannot stress enough how important that is. When you read the problem, you think to yourself, what am I trying to optimize? And by optimize, I mean max or min. Volume, I'm trying to find max volume. I need to write a volume equation. So the next thing I do is I come down here and I write V equals. Because I am trying to write an equation for volume. Now, I put equation slash function because usually when you write your equation, well, what would it be for volume? What comes to mind for the volume of a box? Length times width times height. Right? Now, what's wrong with that? There's too many variables, right? I mean, length, width, height. And so then I guess you could say step 3, right? And this is why the function part is there. We now need to rewrite the equation in terms, and this isn't showing up on the board right now, is it? Rewrite the equation in terms of a single variable. We need to rewrite that equation in terms of a single variable. Now, the way that that happens, and step 3 might be the hardest step of all, depending in the problem. Now, I don't think this one's going to be very hard at all. But sometimes we have what are called primary equations. Well, the primary equation is the thing we're trying to optimize. I think your book might call it the objective function. Okay, the objective function, because that's the objective in this problem. Or the primary equation, that's the thing we're trying to maximize or minimize. And then when we get to step 3 and we need to get it in terms of one variable, we have to take other information in the problem then to help us do that. And sometimes that involves the use of secondary equations or just other information that helps us get it down to one variable. Now sometimes it just happens automatically, it's very easy, and then there are other times where that's a little more difficult. Okay, and so that's what makes some of the problems easier than others. Now I said this was going to be an 8.5 by 11 sheet of paper. And I'm going to cut squares, and that's what the problem says. They're going to be squares, and they're going to be 4 equal squares that I'm going to cut out. And then I'm going to fold that up to make my box. Okay? So what do I do from here? Bring out some, and where do you want to put the X?
Like on the length of the corners.
Like right here?
Yeah.
Since these are squares, right, every one of those would be X. You want to pick X, that's fine. Now, somebody else might be looking at it and thinking, what else could you call that? Isn't that H? I mean, when you fold up those corners, that will be H too, won't it? So you can use H and use X, but since he recommended this, let's do it with X. That's fine. A lot of times you do that. A lot of times you don't. Your variable you end up with isn't even one of the variables in your original equation. It's something else, okay, that you put in, and that's fine. All right, so here we go. So what's the length? Let's call this the length down here. What's the length of our box? That'd be this piece right here. What? 11 minus 2x. So our length is 11 minus 2x. Our width? 8.5 minus 2x. That would be this width right here. So 8.5 minus 2x. And our height? Very good. So that wasn't too bad. I mean, just has it label something in the picture and then write it. So that really was not too bad at all. And so we've got that. Well, now we are where we needed to be almost when we did them in chapter 2. We now have the thing we're trying to, what did we say, maximize? We're looking for the max of this function. So our list of candidates is going to be V of something and V of something, right? Okay, that's what we're going to be doing for our list of candidates. All right, what do I not have? Endpoints, right? I've got my function that I'm trying to find the max of, but I don't have endpoints. Now, what are endpoints? Well, if you think about the picture we had up here earlier, the endpoints are X values, right? They're input values. It's the littlest input and the biggest input. So that's what needs to be going through your mind when you think of endpoints. You need to be thinking, what's my littlest input? What's my biggest input? So we come back to this, and of course my input is X. So I look at my picture and think, what's the littlest input I could have? 0. Now, we could argue about whether you could really have 0. If X is 0, you don't even have a box, right? Of course, which means your volume is 0. So that'd be your minimum, wouldn't it? So we'll go ahead and use it. Even in many real-life problems, the endpoints don't make sense, but we'll still discuss them, or we'll still put them in our list of candidates. They won't be maxes. They won't end up being what we're looking for, but they help us to compare or whatever. What's the biggest X could be? 4.5. 0.25, right? Why is that? That would use up the whole 8.5 side, right? And so then, again, we'd have no volume. It would just fold into a flat, piece of paper, folded up, because the one side we'd have cut all of it out. So you would end up with, so half of 8.5, which would be 4 1/4. So there's my endpoint. So those weren't too hard to find either, but the way you find them is you look at the problem and you think, okay, what's the littlest input I could have? What's the biggest input I could have? There's my endpoints. So now, what do we need to do next? Derivative, right? Now, remember, this is a calculator problem, so all of this would be good to have on your paper, but it is perfectly acceptable for you to now go to your calculator to do that derivative. So let's go ahead and do that. I don't want to, these are going to be hard enough the way it is without muddying it up with a bunch of algebra that we have to do any more than necessary. So I would just do the derivative of that just the way it's written. What do we get?
4x squared minus 78 plus 93.5.
Sounds right? Just did it in my head. That's what I got when I was. Okay. Okay. And now what do we do with that? We ask ourselves two questions. Where does it equal 0? And where is it undefined? Well, equal 0 is something we need to solve. So we go ahead and solve that. So again, make sure you put equal 0 on your paper. If you're going to use your calculator to solve an equation, the equation needs to be on your paper. So make sure you put equal 0. And now go ahead and get into your calculator to solve. What do we get?
1.585
8.5.
more, but and then 4.91458.
So 4.915.
Yeah, that's not in the domain.
But that's not inside of our interval, is it? Now you might not always have noticed that, and you might put it into your list of candidates, and usually what happens is it gives you a value that in this case would be negative, and so you would pretty much know to eliminate that as a max value anyway. And I wouldn't count off if you did include it. However, if you take a value that's not in your domain and you put it in and it does end up being the max and you use it, then that would not be good. And so you probably should get in the habit of noticing that and saying, okay, that's not inside of my endpoints, and so I'm not going to use that. So my list of candidates then, oh, and I'm sorry, I forgot one thing. What about where the derivative is undefined? Is it ever undefined? What would make a function be undefined? The big one is dividing by 0, right? That's the big one. That's the one we usually look for. Now, to be honest, that one happens quite a bit, especially I think your very first homework problem gets into a square root situation. You have a square root of some stuff. Well, when you do the derivative of that, right, that's the 1/2 power. You do the derivative of that, you get, bring the 1/2 down in front, then it's negative 1/2, which puts that on the bottom, right? So you get this derivative, and then of course times the derivative inside. I think on the homework it's like 10x minus 8 over 2 square root something something. That's your derivative. Well, now when you go to ask yourself, where does a derivative equal 0? When does a fraction ever equal 0? When the top is 0. Now, since we have these calculators that are solved, you could set your whole derivative equal to 0 if you want to. but it sure would save you some time in entering. If you were setting this equal to 0, instead of typing the whole thing in, just set the top equal to 0 and solve it. Now, where's the derivative undefined? Well, it's going to be if the bottom is ever 0. So you could just take the bottom and set it equal to 0 and solve that. And that would be where the derivative is undefined, right? But so that's the big one. That's when the derivative will be undefined. Now, you also could say we can't have a negative in the square root. That's true. But if there's a negative inside of this square root, it's also going to be inside the original square root, isn't it? Because you know when you do the derivative, you leave the inside alone. So that's not in your domain anyway. So usually that's not as big a deal. So most of the time it's where the derivative is 0 on the bottom is when it's undefined. And so that's the one to be looking for. But we do need a discussion. So on this one you do need to write v prime is never undefined. Now the reason I'm making you write that is I want you to always consider it. You need, and on the AP test you need to as well, but you need to justify that you have checked all the possible candidates for your max and min. So you need to discuss that somehow. Plus the other thing is most of the problems, you're going to end up writing this. Most of the problems, the derivative is not undefined. But then you're going to happen onto the one problem where it matters, where the derivative is undefined and that matters, and you're going to forget about it. So this way at least you're thinking about it on every problem, so that if that comes up, it won't slip by you. All right, so our list of candidates now is going to be V of 1.585, V of 0, V of 4.25. All right, now I think we're already pretty well convinced that if we put in the endpoints, we're going to get no volume, but it certainly will not hurt to go back and plug those in, right? The vertical bar is a nice way to do that on your calculator mode. And when you plug in the 1.585, make sure you plug in more than 3 decimal places. It may not matter, but you need your final answer to be accurate to 3. Anybody got that yet? Go ahead and do it. Let's see what we get. Pretty well convinced that that one candidate is going to be our max. I think we used a little different number, size paper in the last class, so I can't remember. 50 something maybe. 60 something.
$66.15.
That what you're getting? Anybody else backing up on that? 66 point what?
15.
That's what I got.
15.
What was 1, 4, 8, 2, 3, 4, 9, 8?
So we would want to say 148, right? 3 decimal places. So 66.148. Now, when we were doing max and min problems before, we would just circle that and we would say max. Well, that's not, I mean, we can still do that, and that's fine, but that may not be the end. Okay, these are more realistic kind of problems. They have units, they have context, so we need to answer the question that's asked. So this answer might have, or this question might have been, what size squares should we cut out to maximize the volume? So you would say, well, you cut out squares that are 1.585 by 1.585, right? That was what X was. Or they might say, what is the max volume? And then you would say 66.148 cubic inches, or whatever the units were. So you would have to use units, you would have to answer the question that's asked. Okay? But there it is. I mean, that is an optimization problem. Now, in our list of steps, essentially it's identify the quantity to be optimized, write an equation for that quantity, rewrite the equation in terms of a single variable, and that got us to here, and then we went to this stuff, the calculus part, right? So step 4 is do the calculus, right? I mean, that's where it comes in. I mean, you could add in there, find the endpoints. Maybe step 4 is find, identify the endpoints. Maybe that needs to be in there, okay? And then step 5 is do the calculus part. Answer the question. All right, so my attempt has partially succeeded to give you a little bit more homework time. So here we go. 4.3. The idea, is that if we could get farther into the homework in class and I can help you, and so forth, you can get more of it done and do better, and that's the plan. 5 problems, 4, 9, 11, 17, 22. There's plenty for us to talk about as you get into those, so let's get right into it. And I will help you as you have questions. The very first question refers to an example in the book. I would definitely look at that example for some guidance. That's helpful.